Hello everyone, welcome back to 3 Deviations. So in the last video we talked about the fundamental theorem of calculus, part 2, and that was really helpful for evaluating integrals. What took us minutes in our early videos on integral calculus took us seconds when we could apply the second part of the fundamental theorem of calculus. So that's really helpful. Now we're going to switch gears a little bit. The second part of the fundamental theorem of calculus is not going away for quite a long time, but we're going to switch gears and we're going to talk about the indefinite integral. So we've been talking a lot about definite integration. So definite integration means that our result is going to be a number. We're going to get a value. That value is going to be the area under a curve, and we talked about that quite a bit. Well, now we're going to be talking about indefinite integration, and this is where our output is going to be a function. So another word for this is antidifferentiation, which we covered. So indefinite integration is really just antidifferentiation, as we'll cover right here. So if I use the calculus jargon, when I say I want to take an indefinite integral, it really means I want to take the antiderivative of a function. We talked about that earlier. If I have a function here, if I have f of x, and I have f prime of x, well, if I take a derivative here, if I take a derivative, so if I go d by dx, I'm going to get to my f prime. But then if I do our new operation, the antidifferentiation or the indefinite integral, then I'm going to get my original function f of x. Right, so let's define the indefinite integral a little bit more succinctly here. So the indefinite integral, our notation is just the summa, no bounds. We immediately recognize that it's indefinite because we don't have bounds. If it were definite, we'd have our bounds of integration. But we don't, so that means we're doing it indefinitely. We put our function in there, and then we add a differential at the end. So if I take the indefinite integral of f of x dx, I get capital X. And that's where capital F prime of x is equal to f of x. All right, so if I integrate x squared dx, I get 1/3 x cubed plus c. We add that plus c just because when we differentiate a function, the constant term gets killed, so that goes away. So when we integrate, where we actually have a more general set of curves, and this means really that we can add any plus c, any arbitrary constant. So we call that plus c a constant of integration. Then if I differentiate that antiderivative I just found, then I'm going to get the original function. So if I take d by dx of 1/3 x cubed plus c, well, that goes to x squared. We use the power rule for that monomial, and then the plus c, since that's just a constant, that goes to 0. So we just get x squared again, and that should make sense. That's how our indefinite integral works, and I think this is probably one of my favorite topics in calculus, and we're going to have a unit on that in a while. All right, so now let's cover some of the indefinite integration properties. So if I have an indefinite integral of a constant times a function f of x dx, this is a theme we've been seeing throughout calculus. We could just pull the constant outside, and we can take c times the integral of f of x dx. The important thing is that c is not going to be x dependent, right? So it's just a constant. Also, if I take the indefinite integral of a sum of functions, well, I can separate that as well. So if at the integral of f of x plus g of x dx, that'll just become the integral of f of x dx plus the integral of g of x dx. So that makes it easy. That kind of is like the sum and difference rule that we had in differentiation. It was something that was pretty trivial, but it's still good that we cover it. All right, so now we have another property. This is just a constant property. So if I'm integrating constant k, it's not x dependent, well, I just add a power of x. So that goes from x naught to x to the first power. So I take the integral of k dx. That becomes kx plus c. All right, so now we've covered the basics of indefinite integration. Now I'm going to show you something that is going to be super important for you for the rest of your times in calculus. We are going to do the integration table. So the integration table shows you all of your basic integrals and integral formulas that you need to know, with the exception of a few that we're going to learn about in a new unit coming up in the second half of our course. So we have the integration table. So it's so big we actually need to split this up into two slides. And this is something that most teachers will give a formula sheet for on their tests, but it's also good to memorize these if you're taking an AP or something of that nature. So the first thing on our integration table says the integral, we talked about this earlier, the indefinite integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c, where n does not equal 1. So that's important. That's an important integration topic. So that's our reverse power rule, if we remember that. Now if I take the integral of 1 over x dx, then that becomes the natural logarithm of x plus c. And we have that absolute value as well. And again, we always add that arbitrary constant c. If I have the integral of e to the x dx, then that just becomes e to the x plus c, because if you remember, if I differentiate e to the x, I just get e to the x. So if I reverse that, I'm also going to get e to the x. That should be pretty familiar as well. So then if I have a general exponential, if I have the integral of b to the x dx, then that just becomes b to the x over the natural logarithm of b plus c. Okay, so now if I have the sine of x dx, well, then I can reverse differentiate that and take the integral. That becomes negative cosine of x plus c. If I integrate indefinitely the cosine of x dx, then that becomes the sine of x plus c. Now, these are our core antiderivatives. These are the super important ones. If there's any that you absolutely must remember, it's going to be these guys. Of course, there are going to be some more that we're going to talk about in the second part, but this is the really important integrals that you need to remember. All right, now let's keep on going. So now we're going to do the rest of the trig functions. So if I have the integral of secant squared of x dx, then that becomes the tangent of x plus c. If I have the integral of the cosecant squared of x dx, then that becomes the negative cotangent of x plus c. If I have the secant of x times the tangent of x dx, then that goes to the secant of x plus c. If I have the cosecant of x times the cotangent of x dx, then that becomes the negative cosecant of x plus c. If I have 1 over x squared plus 1 dx, then that becomes the tangent inverse of x plus c. If I have 1 over the square root of 1 minus x squared dx, then that becomes the inverse sine of x plus c. All right, we've got a couple more. If I have the hyperbolic sine of x dx, then that becomes the hyperbolic cosine of x plus c. And finally, if I have the integral of the hyperbolic cosine of x dx, then that goes to the hyperbolic sine of x plus c. All right, so that is our main integration table. This is the second part here. These are also some pretty important ones. These are going to be important in Unit 6 when we do some more integration. So this is really our super important integration table. In the next video, we're going to be back. We're going to do a couple examples with this. We will see you guys then. Bye-bye.